Hey guys, so today we're going to be in Chapter 6, Section 1, which is all about matrix solutions to linear systems. Back in Chapter 5, we did 2 sections of Chapter 5, and it was all over systems of linear equations. We had systems with 2 equations, 2 unknowns, which was 5.1, and we had systems of equations with 3 variables, and that was 5.3. And we learned how to solve those using the addition method and the substitution method. And so really what today is it's learning another way of solving systems of equations, only now we're going to use matrices. And a matrix is an array of information or terms that is lined up in columns and rows within like square brackets. You can see one on the notes that I am sharing with you. So that's what a matrix is. And we're going to use it to hold all of our information for our systems of equations. An augmented matrix is going to separate 2 different pieces of data, really, or information. And what it's going to separate for us is it's going to separate the coefficients within our equations with that of our solutions. So let me show you, because it sounds weird, but really when you see it, you're like, oh, okay. It's just a way of writing a system of equations as a matrix. So here's the first example. I'm not going to do it on the board because really there's not a lot to write. So I'm just going to talk you through it. It says write an augmented matrix for this system, and then it gives you a system of 3 equations with 3 unknowns. The first thing I want you to note, though, as you look at these equations, is that equation number 1, that top equation, does not have an x term. That's totally okay. The one thing you need to consider, though, is just like with synthetic division or long division, we had to put a placeholder in of 0. For like 0x, when we're doing matrices, you also have to do that. So if you're missing one of your terms, you need to put in a 0 there. So if you notice, I write the system of equations again, and this time I put a 0x for that top equation. That way I have a 0 placeholder. After that, notice also that these are all written in x, y, z equals your solution. And if you have an equation that's not written like that, that's the form you want to get it in, where you have the x's and your y's and your z's, because we're going to put them in this augmented matrix where we have an x column, a y column, and a z column, and then our solution column. And then as you read your row is how you read your equation. So that top equation is 0x plus 2y minus z equals 7. So as I make my augmented matrix, I'm just going to look at the coefficients of each of the variables. So my coefficient for x is 0, so that's my first term. My coefficient for y is 2, so that's my second term. Coefficient for z is a -1, so that's my third term. And then I have that vertical bar that is going to separate my equation from the solution that they gave us, which is the 7. So notice that that's on the right-hand side of that vertical bar. Then we're going to do the exact same thing for the next 2 equations. So next equation, I have 1x, 2y, 1z, and 17 is my solution. The third equation, I have 2x minus 3y, 2z, and a -1. So that's how we write an augmented matrix from a system of equations. You should be able to go both ways with this. So if they give you a system of equations, you should be able to write the augmented matrix. If they give you an augmented matrix, you should be able to go back and write the system of equations, noting that first you have your x's, then you have your y's, and then you have your z's. Okay, so there's your augmented matrix. Here is the meat and potatoes of the notes, right here. Let me make my screen just a little bit smaller so you can see all the notes. There. So this is the majority of the notes for today. Before we talk about what we're doing exactly, I want you to see the end goal, or the main goal is to get this row echelon form of a matrix. So if you look at this augmented matrix, notice you have a 1 in your diagonals, you have zeros underneath your 1s, and then you have these A through F letters. These A through F letters are just variables, so those will just be random numbers like 1, 4, 7, whatever. It doesn't matter what those are. That's why they're represented by letters. The diagonal of 1s and then the 0s are what you need to get in order to get to row echelon form. So that is your end goal with what we're going to be doing here in just a little bit. So I wanted to note that there. So here's the 3 ranked matrix row operations that you have at your disposal. Because what we're going to do is we're going to take our augmented matrix from our system of equations. Then we're going to do these 3 matrix row operations to it, maybe more than once. We're going to keep playing around with it until we get this row echelon form. That's our goal. So what are these 3 matrix operations? Well, the first one, you have Ri going to Rj. What this means is that you can flip-flop or interchange 2 rows. We don't change the order of them, like of the numbers within the row. All we're doing is we can flip-flop 2 rows. That's what we can do. The second matrix row operation is K times Ri. We can multiply the elements in a row by any non-zero number. Notice it says non-zero. So it can be a positive number, a negative number, it can be a fraction. We do this in order to get those ones. You see those ones in our diagonal? We're going to use K times Ri to get those ones. Okay. The last of our matrix row operations is kind of the trickier one. It's where you take a constant times the elements in a row, and then you're going to add that to another row. So this Rj row, that second row that's not being multiplied, that's the row you're changing. That's the row that's going to be different. The other row is going to stay the same. And we'll see this in a minute as we work through some examples. But what we do with our number 3 row matrix row operation is we can multiply the elements of a row by a non-zero number and then add it to the corresponding elements in another row. So again, we're going to see that. Really what this is this is us doing the addition method of solving systems of equations just within the matrices. Remember when we did the addition method, sometimes you have to multiply one or both of your equations by a constant, and then you'd add them together to get it to go to 0. Well, that's really what we're doing here with this matrix row operation, because we want to get these zeros in our row echelon form. And you get these zeros by doing this K times Ri plus Rj. That's how we get them. So you're doing the addition method is what you're doing. One additional thing to note is that 2 matrices are row equivalent if one can be achieved from the other by a series of these operations. Basically, if you can get from matrix 1 to matrix 2 by doing these row operations, then they're called row equivalent. You don't really need to know that, but it's good to note. Okay. So let's do an example. Done a lot of talking, so let's do some actual math. Okay, so I slid up the notes so that you could see this example is right there as well in the notes, in case you can't read it at the angle that it is up here on the board. So it says we're going to perform the row operation, and then it gives you a matrix. Now, some of these problems will give you a matrix. Some of these problems will give you a system of equations. If you're given a system, then stick it as an augmented matrix before you start. That's all you need to do for that. A says we're going to take row 1 and we're going to switch it with row 2. So you draw your matrix. And I'm going to switch row 1 and row 2. Now, I'm not messing with row 3, so I'm actually going to start with row 3, and I'm going to write it in to kind of give me my setup, give me my columns, and also just so I don't forget this one or mess it up. So if I'm switching rows 1 and 2, then row 2 is going to be my new row 1. And then row 1 is going to be my new row 2. So when you interchange or switch 2 rows, that's literally all you're doing. You switch the 2 rows they indicate, and that's it, you move on. B says I'm taking 1/3 times R1, which is row 1. So for this one, I'm not changing rows 2 or 3. So I'm going to write those first. 1, 2, 2, -3, But what I am doing is I'm taking every element that's in row 1 and I'm multiplying it by 1/3. So 1/3 times 3 will give me 1. 1/3 times 18 will give me 6. 1/3 times -12 will give me a -4. And 1/3 times 21 will give me 7. Okay, I'm going to slide you over because I know that's small and angled. And you have the starting equation or the starting matrix right there in front of you in the notes that I'm sharing. So I'm going to slide you over to this next one. This last one is the bigger or slightly more complicated of the row operations because you're going to do two different things at once. So for this case, I'm going to show it to you in 2 steps so you can see exactly what's happening. But as we move on in this lecture, I'm going to just do it in 1 step, but I'll talk you through it as I'm doing it, okay? So this says 2 times row 2 plus row 3. So the question is, am I replacing row 2 or am I replacing row 3? You are always replacing row 3, or not always, but in this case, you're always replacing row 3. You're replacing the row that's indicated second or that you're not multiplying by a constant. So the one that you're multiplying by a constant, you're not changing. You change the one that's stuck on here, okay? So if I'm changing row 3, then I can write row 1 and row 2 exactly like it is. But I'm going to leave some space because I'm going to show you what we're doing. And so I'm going to leave some space to show that. Then we have 1, 2, -3, 5. Okay. So what we're doing with this row operation is we're taking 2 times row 2, but we're adding it to the corresponding element in row 3. Okay. So I have 2 times the element in row 2, which is 1, plus the corresponding element in row 3. So that first element in row 3 is a -2. So I'm writing it out long ways this time so you can see what I'm doing. Now I'm going to the next element. 2 times the element in row 2, which is 2, plus the corresponding element in row 3, which is -3. 2 times row 2's element, which is -3. Add to that the corresponding element from row 3, which is 4. 2 times row 2, adding to that row 3. I'm going to come up here to write the simplified answer. So row 1 was 3, 18, that's a big gap. 18, -12, vertical bar, 21. Row 2 was 1, 2, -3, 5. And now I'm going to calculate my new row 3. 2 minus 2 will give me 0. 4 minus 3 will give me 1. -6 plus 4 will give me a -2. And 10 minus 6 will give me a +4. So that's how you do each of the row operations. You'll either flip-flop, you'll multiply one whole row by a constant, a non-zero constant, or you'll multiply a row by a constant and then add that to the element in a different row. Okay, so those are the 3 matrix operations. If you want more practice with those, there is another example in the notes. I don't work through it, but it is written there if you want just another example to work through those. All right, so why in the world do we learn those matrix operations? Well, we learn them so that we can do Gaussian elimination. That sounds weird, but it's just because, sorry. So Gaussian elimination sounds weird, but really it's just because the mathematician who came up with this system or this method is known, his last name was Gauss. So Gaussian elimination is going to allow us to go from an augmented matrix to our row echelon form and thus solve a system of equations using matrices. So there's 4 steps really that you're going to do. The first step is you need to write an augmented matrix for the system that is given. After that, you're going to use row operations to get a row equivalent matrix in row echelon form. So you're going to keep manipulating your matrix until you get that row echelon form where you have the diagonal of 1s with 0s underneath. Then you will write your new system of equations from that augmented or from that row echelon matrix, and you will be able to back substitute to solve for all of your variables. So I'm going to erase the board, and then I will write our example on the board, and then we will give it a shot. All right, there's our system of equations. That is the exact system that you have on your paper as well. And we want to get to the row echelon form. So the first step we're going to do is we're going to write an augmented matrix from our system. That's where we write the coefficients, and then we put the vertical bar where the equal sign is, and we put our solution on the right-hand side. So for equation 1, that'll be 1, 3, 2, vertical bar, 31. For equation 2, that's 1, 1, 2, vertical bar, 19. And equation 3, that's 1, 3, 2, vertical bar, 25. Now I'm going to scroll up a little bit because I want you to see, I wrote in the notes so that you can kind of see what we're wanting. To remind you that the row echelon form has a diagonal of 1s with the 0s underneath. This is what we're going for. Okay, so what does that mean? Well, it means in the upper left-hand corner of our matrix, we want this to be a 1. Now, when it's your very first one, like the top left one, when you're looking for that one, the first thing you want to do is see if you can interchange 2 of your equations first. Because if you can, that's going to simplify things a lot. So I look, and if I look at equation 2, hey, that's got a 1 right there. So I'm going to flip-flop equations 1 and 2. And as we move through this, I'm going to label each of my matrices so that you can see exactly what I'm doing on every single step. So for this first one, I'm going to switch row 1 with row 2. My row 3 is going to stay the same, but that'll get me a 1 in the upper left corner, which is what I need to get started. Because we're going to do row operations, but we're going to go by column. And what I mean by that is when you look at your echelon form right here, notice you have 1, 0, 0 in that first column. So I'm working towards getting that situated first, and then I'll move on to column 2, and then I'll move on to column 3. So I'm doing row operations to get my columns good, okay? So there's row 3. Now I'm flipping rows 1 and 2. So row 2 is going to become my new row 1, and row 1 is going to become my new row 2. So all I did was I flip-flopped row 1 and row 2. Now I have that 1 in the right spot, but I really want to get zeros underneath that. So here's how you get zeros. If you see that you need to get a 0, you're going to use that third method of that third row operation. You're gonna have to multiply one of your rows by a constant and add it to that other row to get that to be a 0. So what do I add to 3 to get to 0? Well, you're gonna add -3. So that means I need to multiply row 1 by -3 and add it to row 2. So I'm going to take -3 times row 1, and I'm going to add that to row 2. And I'm just concentrating on that one right now. So that means my row 1 is not going to change. And my row 3 is not going to change. The only thing that's changing is my row 2. So here's how we figure this out. And you can write it the long way, like I just did on the previous example. I'm going to save my board space and just time and not do that, but I'm going to talk you through how I get every single number, okay? So I'm taking -3 times row 1 and adding that to the corresponding element in row 2. So I'm taking -3 times 1, which is -3, and adding that to +3, which will give me 0. That was what we were doing it for. -3 times 1 is -3. Adding that to +1 will give me a -2. -3 times 2 is a -6. Plus 2 will give me a -4. -3 times 19 is a -57. Add to that a +31, and I get a -26. So I have a 1, I have a 0, but I still need another 0. So just like over here with this 3, I'm asking, what do I add to +1 to get to 0? Well, I'm going to have to add -1 to that. So I'm going to multiply row 1 by -1 and add it to row 3. So negative times row 1, and I'm going to add that to row 3. And I will slide you down. Hopefully. Sorry, it gets a little precarious trying to balance this. So rows 1 and 2 are going to stay the same this time. And it's row 3 that is changing. So I'm taking a negative times row 1. So negative times 1 is a -1. Add that to +1. I get 0. Negative times 1 will give me a -1. I add that to 3. I get a +2. Negative times 2 is a -2. I add that to 2. I get 0. Negative times 19 is a -19. And I add that to 25. I get a +6. Now I have my first column. It's all good. 1, 0, 0. So the next thing I need to focus on is column 2. And the first thing that I need to fix is that number right there. That needs to be a +1. So when we're looking for zeros, we're doing our third row operation where we multiply and then add. When we are looking for our 1s, you're going to think about multiplying just by the constant. That's your second row operation. So what do I multiply -2 by in order to get to +1? Well, let's say you don't know, okay? So I have -2, and I'm going to multiply that by some number in order to get to 1. So really I have -2x equals 1. So to solve for x, I would divide both sides by -2, which would give me a -1/2. That's what I need to multiply row 2 by in order to get that to be a +1. Maybe you're looking at your screen and thinking, well, why in the world wouldn't I just add to it in order to get it to go away? Well, because if you're going to add to it, you're going to have to do this again. Or if you multiply it, then you have to add to it. But that's going to end up messing up your zeros and stuff. So the easiest solution is to multiply by the non-zero constant that's going to turn that into 1. And the non-zero constant that turns -2 into 1 is -1/2. So I'm going to take -1/2 times all of row 2. You don't get to do just an individual element. You have to do the entire row. So don't try and do any magic math like that, okay? I'm going to slide you down so you can see. So rows 1 and 3 stay the same. Do you have to start with the rows you're not messing with? No, but for me, then I make sure that 1, I'm focusing on the right row, and 2, I don't copy down something incorrectly as I'm doing my math. So -1/2 times 0 is 0. -1/2 times -2 is a +1. -1/2 times -4 will give me a +2. And -1/2 times a -26 will give me a +13. Now I have the 1 in the right spot. So I have 1, 0, 0. I have 1 there. So I need to get a 0 here. And just like before, in order to get a 0 there, I need to think, what do I add to +2 in order to get to 0? Well, you add -2. And how do I do that? Well, I'm going to have to multiply one of my other rows. Now you may be looking at both of these, and both of those have a 1 in the corresponding spot. So how do you know whether to multiply row 1 and add it to row 3 or row 2 and add it to row 3? Here's how you know. Here's the hint. If I do row 1 by a -2, like I multiply it and then add it, well, look at the first term. I have to multiply it by -2 and add it. -2 times 1 is -2, and if I add that to 0, I'm messing up this spot right here. So you always want to do it with the row that has a 0 in the spots where it needs to be, so it doesn't mess up the zeros on the row that you're on. Okay, so I'm going to take -2 times row 2 and add that to row 3. Okay, so row 3 is the one that is changing. Row 1 doesn't change. Row 2 doesn't change. Row 3 changes. -2 times row 2. So -2 times 0 plus 0 is 0. -2 times 1 is -2. Add that to +2, you get 0. That was our goal. -2 times 2 is 4, -4. Add that to 0, you get -4. -2 times 13 is a -26. And add that to +6, and you get -20. Okay, we're almost done because we have 1, 0, 0, 1, 0. So we have our first 2 columns done. The last thing we're needing is we need that -4 to be a +1. So just like over here, we had to figure out how to do that, doing the exact same steps over here. So what do I need to multiply -4 by to get it to go to +1? Well, I need to multiply it by a -1/4. But I can't just do that individual term. I have to do the whole row. So I'm going to take -1/4 times row 3. So row 1 doesn't change. Row 2 doesn't change. Row 3 is going to be multiplied by -1/4. -1/4 times 0 is 0. -1/4 times 0 is 0. -1/4 times -4 is 1, and -1/4 times -20 is a +5. Now, we are to the point where we have achieved row echelon form with our matrix. So step number 3 says we need to write a system of equations from this matrix. Remember, the first column was your x's, your y's, and your z's with your solution. And then we had individual equations. So that first row is going to change over into an equation. Let me show you. So we have x plus y plus 2z, x plus y plus 2z equals 19. Equation number 2, we have y plus 2z equals 13. And the bottom equation says we have z equals 5. So we know one of our variables, we know z is 5, so we can back substitute that to solve for y. Then we can back substitute both of those to solve for x. And that's what it means on number 4 where we back substitute. So I'm going to come just down here to do this so that I stay all on the same screen that you're on. So y plus 2z equals 13. Well, z is 5. We just found that. So y plus 2 times 5 is 10 equals 13. So y equals 3. Okay. So now we know a z and we know y. So I'm going to solve for x. X plus y plus 2z equals 19. X plus y, well, y was 3, plus 2 times z, well, 2 times z, 2 times 5 is 10, equals 19. X plus 13 equals 19. So x equals 6. So our solution, our set is the ordered triple, 6, 3, 5. Just like that. So that's how you use Gaussian elimination in order to solve a system of equations. If you look at my notes, I do the exact same steps I just did, and I even highlight the numbers that I'm concentrating on, and I tell you what we need to happen. I do more than one thing in some of my matrices, but I write right next to the row what I did. So instead of writing 2 separate matrices to get those zeros underneath that first one, I did it all in one matrix, but I wrote next to it what exactly I did. Okay, so if you're looking at my notes, it's really straight through, or straight. It's straightforward. That's what I'm thinking. All right. So if Gauss came up with this, well, he kind of partnered up when Jordan came along after him and came up with another way to do it. So we went from our augmented matrix to our row echelon form, and then we wrote our system of equations and back substituted. That's how we do Gaussian elimination. But there is a reduced row echelon form, which is on the notes screen right there in front of you, where instead of just getting zeros under the ones, we get zeros over the ones as well. And what's nice about reduced row echelon form is if you do that, if you get reduced row echelon form, then look, then you get z equals c, y equals b, and x equals a, because there's no need for back substitution because you've already solved everything. So that's what's really nice about reduced row echelon form. And so if we did that, it's called the Gauss-Jordan elimination method. So you do everything exactly the same, only once you get to the row echelon form, we're not done. We have to keep going to get to reduced row echelon form. We still do everything the same way. You want to get to row echelon form first. So you want to get that diagonal of ones with the zeros underneath, and then you want to concentrate on those top zeros, okay? So if you're going to do Gauss-Jordan, if it specifies Gauss-Jordan on a test, you write the augmented matrix for your system. You use the row operations to get to reduced row echelon form instead of just echelon form. Then you write the system from that matrix, but you don't have to do any back substitution because you're going to have x equal a number, y equals a number, and z equals a number. Okay, so instead of doing a whole new problem, we're going to continue with the problem we just did. So I know we already solved it. We got 6, 3, and 5. But we're going to just continue with it so that you can see that you still get the exact same answer. And then we don't have to start all the way back at square one for this problem. Okay? So I'm going to rewrite this, our row echelon form, and then we're going to continue on with it, okay? So let me put up a marker. 1, 0, 1, 1, 0, 2, 2, 1, 19, 13, and 5. But you can't see any of that, so let me bring you over. All right, there is our row echelon form. So pretend we just started this problem and we worked all the way through and we got to row echelon form, but we're doing Gauss Jordan. So we got to get reduced row echelon form. So what we're missing is we're missing zeros all over here. That's what we're missing. Now, just like with Gauss getting to row echelon form, we focused on columns. So column 1 is good to go. Column 2 is almost good to go, but we're missing like that zeros kind of our problem. We need to fix it. So what do we add? Remember, when we're using zeros, you want to use that third row operation. We're going to multiply another row and add it to that row. So what do you add to 1 to get you to 0? Well, you add -1. So if I'm looking at my other rows, if I multiply 0 by a number, it's not going to change it. So I'm going to multiply row 2 by a negative and add that to row 1 in order to get a 0 up there. Okay? So row 2 and row 3 are going to stay exactly the same. Now I'm taking negative times 0, negative times row 2, and adding it to row 1. So negative times 0 is 0. Add that to 1, you get 1. Notice it didn't change anything, and that's the goal. We don't want to mess up what we already have accomplished. Negative times 1 will be a -1. Add that to +1. That'll give me 0. Negative times 2 will give me a -2. Add that to +2, and I get a 0. Negative times 13 is a -13. Add that to 19, and I get 6. So notice, even though we were really only concentrating on this 0, this one, we got a 0 here too, which is what we needed too. So that's like a bonus 0. So we don't have to solve for that one now. So that's really nice. So we only have one spot left to solve for, which is right there. So again, we need that 2 to be a 0. So what do you add to 2 to get you to 0? You add a -2. Well, if I multiply row 1 by something, by -2, that's not going to get me there. I need to multiply row 3. So I'm going to multiply row 3, whoa, that's a B, row 3 by -2, and I'm going to add that to row 2 because I need to change row 2. So row 1 stays the same. Row 2 or 3 stays the same. And now I'm concentrating on row 3. I keep saying row 3. Row 2. Concentrate on row 2. -2 times 0 is 0. Add that to 0 and I get 0. -2 times 0 is 0. I add that to 1, I get 1. -2 times 1 is a -2. I add that to +2, I get 0. -2 times 5 is a -10. I add that to 13 and I get a +3. Now I have reduced row echelon form. And notice what's in my column right here. 6, 3, and 5. We had found our solution to be 6, 3, and 5 when we did it just a minute ago with Gaussian elimination. Because what we have right here, this says our first, like if we're writing our system, we have x equals 6, y equals 3, and z equals 5. Or you have your solution set 6, 3, 5. So Gauss-Jordan is actually really, really nice because it goes ahead and completely redoes it for us. Like it simplifies it out all the way to where our answer is right there in our last column. That's pretty awesome, I think. And that is also the end of 6.1.